Hello everyone, a very good evening to all. So today is the last interaction session. I welcome you all again to this interaction session, which is based on the course Atomic and Molecular Physics. And this course is being taught by NPTEL, which is a national program on technology and enhanced learning. In this January 2024 session, the course code is NOC24 PH04. So today will be Since we have in the past interaction sessions, we have discussed few sample problems which were based on that week's lecture or lecture content of the course. So in this interaction session, I'll be basically, in place of solving problems, I'll rather give an overview of the total course what we have studied in this course. And basically, it will be some sorts of a revision, which will definitely help you for your preparation for exams. So once again, myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So let's start our discussion. So initially, if you talk about the course conference, initially we studied about different experimental observations and theoretical developments, and those were related to the discovery of constituents of atoms. The discoveries of constituents of atom. So we know in an atom there is a nucleus which is centrally spaced and it is quite heavy, so that all the approximately all mass of the atom is concentrated at that nucleus only. So atom has a nucleus and electrons are revolving around the nucleus. So the nucleus, it contains protons and neutrons. So we studied about the discoveries which led to the discoveries of electrons, discovery of protons and neutrons. Now talking about the structure of atom, because why we need the why need why we need to know about the structure of atom, because in order to explain different properties or chemical physical properties, we need to describe how the atoms are behaving. That means how the constituents of an atom is behaving. So its constituent basically describes its structure. So motion of the electrons and nucleus describe the atomic structure. But if you consider the mass of nucleus and mass of electron, since the mass of electron is very light in comparison to the mass of nucleus, we can assume that the uh, nucleus is initially at rest, and all the theories that were developed were based on the fact that nucleus is at rest and electrons are revolving around the nucleus. So there are different theories. First, there was Thomson's model of atom. Thomson's model of atom. Basically, this was a plum pudding model, and the pudding was the positive. So basically, according to Thomson's atomic model, the electrons were arranged in a positively charged sphere. So this model is also called as plum pudding model. But this was a very basic model and it could not explain many physical and chemical properties of the atom. So this was discarded. Um, However, the fast in detailed atomic structure, which was accepted up to some extent, was Rutherford's atomic model. And along with the Rutherford's atomic model, Rutherford also discovered the nucleus. So, in case of Rutherford's atomic model, he discovered the nucleus, discovery of nucleus through alpha particle and gold foil experiment. So, using his hypothesis or the experiment, he gave different hypotheses like how the electrons are arranged. So for the first time, he said that electrons are not revolving in an arbitrary orbit. Electrons are revolving around the nucleus in certain circular orbits, basically. After some After a few years, it was changed that electrons are not revolving in circular orbit. By the way, they are revolving in an elliptical orbit. So there are different levels. But if you talk about the stability of the nucleus, Rutherford's atomic model would not explain the stability of the nucleus. Stability of the nucleus, Rutherford's atomic model could not explain. So this model was not accepted up to full extent. Then an in-depth structure of the atom was described by Neil Bohr, and this is known as Bohr's structure of atom. Basically, according to Bohr's principle, what was the two assumptions or two theories that Bohr gave? According to Bohr, he said that electrons are revolving in certain elliptical orbits, and how he explained the stability. He explained that we know for any type of circular motion there is a centrifugal force and centrifugal force. So he said that the centrifugal force which is required for the circular motion of electron around the nucleus is being balanced by the Coulombic interaction between electron and the nucleus. We know in case of atom as a whole is neutral, but electrons are negatively charged and nucleus is positively charged. So since electron and nucleus are separated by some distance because electron can't exist inside the nucleus. So there is some distance between them, and due to that distance, since in case of Coulombic interaction, the range of Coulombic interaction we know it is infinite. So if they are being placed at some finite distance, there will be some force of attraction, and that force of attraction was balanced by the centrifugal force, and due to which there was circular motion of electrons around the nucleus. So there was Bohr's theory. So what Bohr said, he said that the centrifugal force, that is mv square by r, is equal by the Coulomb force of interaction between the nucleus and the electron. So here Z is the atomic number. So also there is another principle. He said that electron can't revolve in all energy levels or on all circular orbits. The electron can revolve in some particular energy levels where the angular momentum is also quantized. So after the evolution of quantum mechanics, Bohr used the principle of quantization of angular momentum, and he said that the angular momentum of electron in certain energy level is given by n h cross, which is n h by 2 pi, where n is integer. So basically mvr, we know the expression for angular momentum is mvr. So mvr is equal to nh by 2 pi. So if you use these two formulas or these two equations, then from these two equations we can derive the velocity of electron in certain energy level, then the radius of that level, and then the overall energy of the electron in that particular level. So according to Bohr's theory of hydrogen atom or hydrogen-like atom, he said that the velocity of electron is Jd square by 2 epsilon 0 nh, where n is the energy level, that is 1, 2, 3, 4 you can put. Then R is n square h square epsilon 0 n square h square epsilon 0 by Jd square pi m, and the fast Bohr orbit, which is also called as Bohr radius, it was found to be 0.53 angstrom. So R naught, which is Bohr radius, that is the basically R naught means, sir, it is not R naught, it is R1 because n equal to 1, and this is Bohr's radius, which is otherwise called as A0, and its value is 0.53 angstrom. So it is the radius of the ground state of the hydrogen atom, because if you put Z equal to 1, only then you can get the value of A0. And if you talk about the energy of the electron in an energy state, then En is minus 1 by 8. So you calculate both the kinetic energy and potential energy. If you put these expressions in the expression for energy, you will get the total energy given by minus 1 by 8 m z square e force by n square h square epsilon 0 square. So the energy was proportional to 1 by n square and the ground state energy. So basically, if you calculate and put all the values, you will get it is minus 13.6 kiloton volt, and there is Z square by N square. So if you put Z equal to 1 for hydrogen and N equal to 1 for the ground state, then you get the energy is minus 13.6 electron volt. So the ground state energy of hydrogen atom is minus 13.6 electron volt. So why it is negative? So it is a bound system, and there is a force of attraction between the nucleus and the electron. So the energy is negative. So as you can see, it is inversely proportional to n square. So as you go away from the nucleus, that is, if you increase the number of levels, then you can get different values of energy levels. And we found that the energy levels are not equally spaced. N equal to 1, then n equal to 2. Then the difference between these two is larger than the difference between n equal to 2 and n equal to 3. So as you go to higher value of n, so at n equal to infinity, basically, this is a continuous level. Because at n equal level, E becomes 0. So there are some concepts related to the potential energy or ionization potential. So basically, ionization potential is nothing but the potential or the amount of energy that is required to remove the electron from the hydrogen atom. Remove means from n equal to 1 to n equal to infinite or 0. So the ionization potential of hydrogen is called as plus 13.6 electron volt. Because if you see at n equal to infinity, E infinity is equal to 0. So minus 13.6 plus 13.6, it will give you 0. So if you provide plus 13.6 electron volt of energy to an electron which is revolving in the ground state of the hydrogen atom, then it will be completely free from the region where it can experience the force of attraction due to nucleus. So these are few things, and uh, after the introduction of these energy terms, then we found that there are some transitions. If the electron goes from higher level to lower level, then it emits some radiation, or if the electron goes from lower level to higher level, it absorbs some radiation. So if you compare, then we can say E is equals to h nu, or you can say hc by lambda, or hc nu bar, where lambda is the wavelength of radiation, nu is the frequency of radiation, and nu bar is the wave number. So basically, the spectra are represented in wave number unit, that is centimeter inverse. And after that, after discussing all these things, so basically, what was the expression for this wave number? So the expression for wave number was R infinite Z square 1 by Ni square minus 1 by Nf square, where R infinity is called as Rydberg's constant, and its value is around 1.097 1.097 into 10. Its value is 1.097 into 10 to the power 7 meter inverse. So these constant, and if you see in the expression of this constant, we have taken only the mass of electron, and we have considered that the nucleus is at rest. So if you take the nucleus, if you don't assume that the nucleus is at rest, then there will be reduced mass of both electron and nucleus system. So if you calculate that, then the Rydberg's constant value is changed. And what is that value? So the actual value will be R infinity divided by 1 plus small n by capital N, where small n is the mass of electron and capital N is the mass of nucleus. So now, if you consider about this Ni and Nf, so if Ni is equals to 1, so if Ni is equals to 1, then it gives Lyman series. Then if Ni is equal to 2, then it gives Balmer series. Then Paschen bracket. Then 5 is Clifford series. So this is nothing but the structure of hydrogen spectra. So it is hydrogen emission spectra. And this Balmer series corresponds to visible region. This series corresponds to infrared, and these are, so this series corresponds to ultraviolet. Then these are infrared, near infrared, far infrared, like that. So as you uh, so as the course continued, then we discuss about the vector atom model. That is, in case of vector atom model, all the quantities were represented in terms of vectors. That is the orbital magnetic moment, orbital angular momentum, all these things. So what we calculated, we know the expression for magnetic moment mu is. So we are talking about vector atom model. So we know mu is equals to I into A, where I is the current and A is the area. So if you calculate, we found that the mu L by L vector mod, mu L vector mod by L vector mod is equal to E by 2m, and this E by 2m is called as gyromagnetic ratio. And if you write it in terms of lambda g factor or orbital g factor, then we can write it as mu L vector is equals to minus GL mu B by H cross into L vector. So here mu B is E H cross by 2m mass of electron, and this is known as Bohr magneton. And this Bohr magneton is the unit of magnetic dipole moments. And this value of GL is 1, which is orbital G factor. And we found that due to this, since due to the orbital motion of electron, there is orbital magnetic dipole moment. So this due to this orbital magnetic dipole moment, it will experience some torque, and this torque will lead to, when an atom is placed in the external magnetic field, this torque lead to the this torque will help to the precision of this orbit around the magnetic field. So this is called as Larmor precision. So in case of Larmor precision, what happens? There is a, so when there is a magnetic field is applied at along certain axis, then there is a rotational motion of the electron orbit about that axis. This is called as Larmor precision, and we calculated the frequency of Larmor precision, and it was EB by 4 pi m, where B is the magnetic field, and suppose this is B, then this is L. This L will precede, so that the value of theta remains constant. This is called as Larmor precision. Then corresponding to the Larmor precision, then since this L vector precedes around the magnetic field, uh, so this is the concept of Larmor precision. We gave an idea about the interaction of atomic dipole moment or the motion of electron with respect to the magnetic field that is applied. And if you consider about the component which is acting along the magnetic field, then this is the component is Lz, and this Lz is nothing but ML H cross, and L vector is L into L plus 1 root over H cross. So these are quantum mechanically given. And then there are concept of space quantization. Like if you are talking about the value of L, then there will be different orientations of L corresponding to the magnetic field, and the component of the component of angular momentum along the magnetic field called as Lz, and the distance between and the angle between the two components is given as cos inverse ml by L into L plus 1 root over. So basically these two things were used here to get the angle of theta. And if you see, so if L is equals to 1, then ML will be having three values, plus 1, 0 and minus 1. So there will be three possible orientations of the orbit with respect to the magnetic field if the atom is placed in an external magnetic field. So then then we also talked about the Stern-Gallath experiment, and this Stern-Gallath experiment helped to discover the space, discover the electron spin, and what the experimental performed, how the experimental performed. So the silver atom was placed in an oven, and the silver atom, the beam of the silver atom was passed through non-uniform magnetic fields. So in case of why the non-uniform magnetic fields are used, because in case of the non-uniform magnetic field, it will experience some bending force, so that due to the different due to the different spin of the electron, there will be two different spin magnetic moments, and these spin magnetic moments, when they are placed in an non-uniform magnetic field, they will experience some bending force, so that we obtained that the single beam was splitted into two beams. So we got some characteristics like that, like this only. There are two beams, and if you see the fluorescence screen, then there was one line above and one line below. It was found that since the in case of silver atom, if you talk about the ground state or the valence electron, then the electron goes to s orbital, and in case of s orbital, the value of L is 0. So there is only spin of electron. So since this was 2, so 2s plus 1 is equal to 2. So we found that s is equal to half. So electron spin, so electron is a spin half particle. We concluded from that experiment. And this experiment also helped to verify the concept of space quantization also. Since the value of s is half, so there are two ms values, one is plus half, another is minus half. So corresponding to these two ms values, we are getting these two spots. One corresponds to plus half, another corresponds to minus half. So similarly, like the relation of gyromagnetic ratio in terms of in case of orbital motion, in case of spin motion also we can write mu s z is equal to minus gs mu b by h cross s vector, and the value of gs is 2, since the electron has two different spins, like spin up and spin down. Now if you put the values and you calculate, then you can get mu z is equals to plus minus mu b. So what we can get from this? So basically, if the electron is revolving in an s orbital, then the magnetic moment of that electron along the magnetic field is equals to the value of the Bohr magnetron, and the value of Bohr magnet is E h cross by 2 m e, where m e is the mass of electron. Now after going through this concept, then we talked about the concept of fine structure. So how the fine structure come into picture? So before talking about the fine structure, let's I think we have missed the concept of Sommerfield's modification to the Bohr's theory. Basically, what happened to the how what did the Sommerfield do? Basically, he modified the Bohr's theory, and he said that no, not the energy levels are not circular; they are basically elliptical, and not all energy levels are circular. There are two quantum numbers he introduced. One was k, another was n. So for that level, only when the value of k is equal to the value of n, then there was only circular orbits. So now now if you talk about the fine structure, then we talk about the spin orbit interaction, that is LS coupling and JJ coupling. So basically in LS coupling, what happens? In case of LS coupling, there is spin and or spin angular. So there is spin angular momentum corresponding to spin motion of electron, and orbital angular momentum corresponding to orbital motion of electron. So when in case of smaller atoms, the spin and orbital angular moment of electron interact with each other, and that result in the modification of the energy system or the Hamilton of the system, and that results in the spin orbit splitting of the of certain elliptical orbits. So what we obtain? We generally, in case of LS coupling, suppose there are two electrons. One is L one for one electron, the orbital angular momentum orbital quantum is L1 and another L2, then the L will be L1 plus L2 up to L1 minus L2 mod with 1 increasing. So basically this is vectorially added, and then S1 and S2 they will add to give S1 plus S2 to S1 minus S2. So now if you talk about electrons and if you talk about more than one electron and more than two electron also. So in the course we also discussed about a few concepts which was related to the number of spectroscopic terms that may rise due to the number of electrons present in the energy level. Sorry. So there was also concepts about equivalent electron configuration and non-equivalent electron configuration. So, and in case of JJ coupling, what happens? In case of JJ coupling, the individual electron, the L and S get coupled to give you the value of J. Then this J and J coupled to give you the value of total J. So this is called as JJ coupling, and it occurs in case of heavy atoms. And in case of light atoms, there is LS coupling. Then after the concept of LS coupling and JJ coupling, then there was a few lectures which are based on the quantum mechanical treatment of hydrogen atom. Then so with that concept, we learned about the concepts of quantum mechanics. In case of quantum mechanics, there was a quantity which was pretty much which pretty much important in case of quantum mechanics, like the quantity which is called as wave function, and using this wave function we can get a lots of information about the system. So then this wave function, then there are the Schrodinger's wave equation. Then the Schrodinger wave equation nothing but h psi equals to e psi. Then we talked about the eigen values, eigen functions, then average values. Then we discussed about the concepts of normalization, orthogonal. All these things are discussed in the topic of quantum mechanical treatment of hydrogen and hydrogen, quantum mechanical treatment of hydrogen atom. Then after the concept, there was also some there was also some concepts which were based on the alkali spectra. Then we also discovered about the sodium spectra. That is, there are differences like principals, sharp, diffuse, fundamental, depending upon the method of transition. In case of the selection rule is delta L is equal to plus minus 1. So sharp series corresponds to NS2 NP, that N is equal to greater than 2, NS2 2P, N equal to greater than 2. Then there is principal series, then there is diffuse series, then there is fundamental series. So it was NP to 1S, N is greater than 1, ND to 2P, N is greater than 2. There is NF to 3D, N is greater than 3. So then we talk about sodium fine structure. In case of sodium, if you see there was a single line, then we talk about the D1 and D2 line. So what are those? Suppose this is 2s level and 2p level. Due to spin orbit interaction, this 2s level was not splitted, it was 2s half, but the 2p level splitted into 2p half and 2p 3 by 2. So the line from 2p half to 2p 3 by 2. Suppose this is 2p half, this is 2p 3 by 2. So the transition from 2p half to 2p 3 by 2s half is called as D1 line, and the transition from 2p 3 by 2 to 2s half is called as D2 line. So after this, we also discuss about the concept of Zeeman effect and star effect. Basically, when an atom is placed in an external magnetic field, then the spectral lines are also getting splitted due to the interaction of the due to the interaction between the spin and orbital angular momentum and the magnetic field. And so we again found that this D1 line was splitted into 4 components and D2 lines are splitted into 6 components. there are the two different types of G-man effect. One was normal G-man effect, another was anomalous G-man effect. In case of normal G-man effect, one single spectral line was being split into three spectral lines. And the normal G, in case of normal G-man effect, the spin of the electron was not considered. That is, S was equal to 0. So only the energy levels are splitting on basis of their value of L. However, in case of anomalous G-man effect, the spin of electron was considered, and the and a single spectral line was being split into a number of spectral lines, more than three spectral lines. So these are some, and also the separation between the labels was also the expression is similar to the Larmor frequency expression. It is EB by 4 pi m. This is called as G-man shift. Then there was Stark effect. Basically, what happens in Stark effect when an atom is placed in external electric field, then the spectral length gets split into a number of components. That is called a Stark effect. And in the concept of G-man effect, there is another concept which is called as Passenberg effect. So when the atom is placed in a strong magnetic field, then the coupling between the spin and orbital angular momentum is broken, and they both persist independently around the magnetic field. So the splitting is different in that case also. So after the G-man effect and Stark effect, then we discussed about the concept of molecular spectroscopy. So if you talk about the concept of molecular spectroscopy, then there are, we know in case of a single atom, there was only electronic spectra. But if you talk about the diatomic molecules, then there is electronic spectra, then there is rotational spectra and vibrational spectra. Rotational spectra and vibrational spectra. So if you talk about the energy of these spectra, electronic spectra, basically the energy is in terms of 0 to 10 electron volt. In case of rotational spectra, in case of vibrational spectra, the energy are in terms of 0.1, are in the order of 0.1 electron volt. And in case of rotational spectra, the energies are of the order of 10 to the minus 3 electron volt. So corresponding to each electronic level, there are a number of vibrational levels, and corresponding to each vibrational levels, there are a number of rotational levels. So electronic spectra corresponds to visible and UV region. Vibrational spectra corresponds to infrared region, and rotational spectra corresponds to microwave region of electromagnetic spectrum. So now there are two type of molecules. One is the diatomic. If you talk about the diatomic molecules, then they can be classified into two types: homonuclear diatomic molecule and heteronuclear diatomic molecule. Like if you talk about carbon monoxide, carbon and oxygen both are different. So these are heteronuclear diatomic molecule. But if you talk about hydrogen, H, both are same. So this is called as homonuclear molecule. So in case of homonuclear diatomic molecule, they don't show the rotational and vibrational spectra or vibrational motion because the both are same. But in case of heteronuclear molecule, they show rotational and vibrational spectra. Now, if you talk about the rotational spectra, in case of rotational spectra, the energy levels are given. So in case of rotational spectra, we considered the concept of rigid rotator, and we found that the energy levels are given in terms of Ej is equals to J into J plus 1 H cross square by 2I, where I is the moment of inertia, and J is the value of rotational quantum number 0, 1, 2, 3. After that, then if you talk about the change of unit, then EJ can be written in terms of J into J plus 1 BHC, or EJ by HC will be B J into J plus 1. So this B is called as rotational constant, and the expression for B is H by 8 pi square IC. So we have solved numerous problems related to the calculation of this rotational constant. How we can calculate if the value of rotational constant is given, how we will calculate the value of I, which I is the moment of inertia, the value is mu r square. Mu is the reduced mass, and r is the bond length, basically. This type of concept we have discussed a number of times. Then correspond to each value of j, then the value correspond to each value of j, then if you say the value of, if you put the value of j equal to 0, then E0 is equal to 0, E1 will be 2 BSC, E2 will be 6 BSC, like that. So if you draw the rotational levels, you can see if the difference is 2, but here the difference is 4. So the rotational levels are not equally spaced. They are not equally spaced. And if you talk about the spectral lines, the spectral lines are equally spaced, because if you talk about the transition between the two levels correspond to J, and the selection rule is J is equal to delta is equal to plus minus 1. And also there was a concept of isotope effect. So since the value of B depends upon, if you talk about the relation, it is 8 pi square I C. I basically we can put mu r square C. So it is inversely proportional to the reduced mass. So in case of isotope, the mass changes, so the value of B can also be changed. And if you talk about the concept of non-rigid rotator, in case of non-rigid rotator, what we obtained, the energy expression was given by the equation E is equal to J into J plus 1 BHC minus J into J plus 1 square DHC. So this was due to the vibrational contribution. So when the bond length is not same, then the bond length will vibrate, and due to that there arises the concept of non-rigid rotator. And we also, it would be then E0 will be 0, but E01, because there are two, then E01 will be 2 BHC minus the contribution will come from this term 4 DHC. So the energy levels are being reduced. So if you talk about the energy level spacing, the energy levels are unequally spaced, and the energy of the rigid rotator level always lies above the energy level of non-rigid rotator, because the energy value is reduced in case of non-rigid rotator due to this vibrational contribution. And after the concept of rotational spectra, then we also discussed about the vibrational spectra. In case of vibrational spectra, that we consider the effect of simple harmonic oscillator. And if you talk about the simple harmonic oscillator, we can say that the potential energy is given by half kx square, which is x minus x0 square. Where x0 is the point of equilibrium. If you take x0 equal to 0, that is origin, then we can write it as Vx is equal to half kx square, where k is the force constant. And we solve a number of problems related to the value of k, and we can say that omega is equal to k by mu root over, where mu is the reduced mass, or you can say the frequency of vibration is 1 by 2 pi k by mu root over. And we have solved number of problems related to the concept of this calculation of the force constant. Then you talk about the energy levels. We know the expression for energy given by V plus half h cross omega, where V is 0, 1, 2, 3, like that. So if the U1 is half h cross omega, which is called as the 0 point energy, and it is the minimum energy of the vibration energy can never be zero. And if you talk about different energy levels, then one will be half h cross omega, then 3 by 2 h cross omega, then 5 by 2 h cross omega. So if you see the difference, it is h cross omega. Here it is also h cross omega. So the energy levels are equally spaced. And since the energy levels are equally spaced, if you apply the selection rules, it is del V is equal to plus minus 1. You will see for all the cases, you will get the value of wave number is plus minus omega E only. So there is a single spectral line corresponding to the vibration energy transition. So in case of vibration spectra, the vibration energy levels of harmonic oscillator are equally spaced, and there is only a single intense spectral line with the wave number which was discussed. Omega E is 1 by C2 pi, because this is wave number unit. So C will be in the denominator. So it is 1 by 2 pi C A by mu root over. So after the concept of harmonic oscillator, then we also discussed about the concept of anharmonic oscillators. In case of anharmonic oscillator, there is another term corresponding to another term contribution to the harmonicity or anharmonicity. It is called anharmonicity. Basically, Vx then it can be written as 1 by x minus x0 square del square v by del x square at x equal to x0. This is the Taylor expansion of the Vx about the equilibrium point. Then it will be 1 by 6, that is 3 factorial, x minus x0 q del q v by del x q at x equal to x0. So this term again gives rise to, if you talk about the energy levels correspond to different vibrational quantum numbers, then the value of energy given by v plus half h c omega e minus b plus half square hc omega e xc. So this omega e xc is called as anharmonicity. And corresponding to the different values of v, we calculated different energy levels. And if the transition occurs from 0 to v, then the wave number corresponding to that particular transition given by v minus e0 by sc. Then if you see the selection rules, then the selection rule for the vibrational transitions is delta V is plus minus 1, plus minus 2, plus minus 3, like that. So for plus minus 1, this is called as fundamental line. For plus minus 2, this is called as fast overtone. Plus minus 3 is for second overtone, like that. So if you, so let me add some slides first. So if you talk about the transition from 0 to 1, then the wave number corresponding transition is given by omega e into 1 minus 2xe. So we solved a few problems related to these relations. And then there is a formula for getting the value of getting the value of number of quantized levels, and this is called as Vd plus 1 equals to 1 by 2hc. We also solved a few problems related to these concepts. Then there are rotational vibrational spectra where both vibrational and rotational energy levels were considered. After that, at the end, we talked about the concept of Raman spectra, Raman spectroscopy. So in case of Raman spectroscopy, what happens when a monochromatic light is incident on an organic liquid, then light scattered in all directions, and it was found that frequency of the scattered light was different that of the incident light. And if the frequency of scattered light was same as the frequency of the incident light, then it is called as relay scattering or elastic scattering. But if the frequency of scattered light is different that of the incident line, then the Raman spectral lines are observed. These lines are called as Stokes and anti-Stokes lines, and the effect is called as Raman effect. And the change in frequency is given by nu is equals to nu minus del nu, where this nu is the incident light. So when del nu equals to 0, then nu prime is equals to nu, and this is called as relay line or relay scattering. Relay line. Then if del nu is greater than 0, then nu prime is greater than nu. Sorry, nu prime is less than nu. So there is transfer of energy from the light to the organic liquid. So the frequency is decreased, and this line is called as Stokes lines. And if the value of delta nu is less than 0, then nu prime is greater than nu. So there is transfer of energy from the organic liquids or the liquid molecules to the light. Then these lines are called as anti-Stokes lines. And if you talk about the spectra, then the spectra was like that. The intense line was relay line. Then there was Stokes line, and then the right hand side there was anti-Stokes lines. And if you talk about the concept of Raman's rotational, rotational and vibrational spectra, then we can find that the intensity of these lines, the intensity of relay line is highest, and then there is intensity of Stokes line and the intensity of anti-Stokes line. And if you talk about the rotational Raman spectra, in case of Raman spectra, the selection rule is delta J is equals to plus minus 2, and due to this we have different uh, spacings as that of the normal rotational spectra. So basically, in case of Raman spectra, the central line is placed at 0, and then the anti-Stokes lines, they are placed at the positive L, that is 6B, then 10B, like that. So they are spaced 4B. Similarly, here the Stokes lines are at minus 6B, minus 10B. So also the separation is 4B. But in case of normal spectral lines, the case of pure rotational spectra, the distance of the separation was only 2B. So in case of Raman rotational lines, these lines are equally spaced, and the spacing is 4B, that is twice that of the rotational line. So this was all about the concept that we covered in the course Atomic and Molecular Physics. This January 2024 session. I hope this will help you in the preparation for your exam. I again thank you all for this. So once again, I thank you to all of you for being registered in this course, and all the best for your future exams. That's it from my side.